I hope my screen is visible to everybody.
Yes, sir.
Okay. So we will start now. So we have completed the Rayleigh Ritz method, and we have seen how to solve or how to analyze the beam problems as well as the bar problems. Okay. Uh, so before starting the new topic, let me tell you two more things about the Rayleigh Ritz method. So we will take two short examples. We won't be solving the full examples. We'll see very short example, and I hope you can do it further. Okay. So for example, let us say I am going for a simple beam. Okay. Rather I'll go for bar first. Beam वाला problem हम लोग बाद में करते हैं. Okay, so let me take a bar. Now this bar is having a varying cross section. Okay, till now whatever problems we have done, in that what we have assumed that the cross section across the length, it is exactly same. Okay, but this time what we will do, we will assume the cross section is different. Okay, so let us say we have a cross section area over here. This is 2 times area and this is only area. Okay, so this is the situation in front of us, right? So now how to handle this particular situation, right? Just for example, let me take this value as L1. Okay, so let me write here. Okay, sorry, let me take this. Okay, so this is your L1. Okay, and this will be your L2. Okay, so let me write down over here. So this is L1 and this will be L2. Okay, just for numerical values, let me take a load which is acting at the center over here. Okay, so it is acting at the center, so let me keep it over here, and its value is, let us say, 3 kilonewton. Okay, so this is what I am assuming over here. Right now in this particular question, what I am doing is I am assuming the value of elasticity for both the section, it is constant. Okay, only the cross section area is changed. So if E is also changed, then also you can solve the problem accordingly, right? So now let us say we want to analyze this particular problem with the help of Rayleigh Ritz method. So what we generally do, first of all, we need to assume a displacement polynomial function. Okay, so let us assume the displacement polynomial function as u equals to a0 plus a1x plus a2 into x square. So I'm just going for a very simple displacement polynomial function, and with this polynomial function, let me draw a simple free body diagram of this particular problem. Okay, so let us call this as, say, node number 1. So in the center we have node number 2, and at the end we have, let us say, node number 3. Okay, if you want, you can even use 0, 1, 2, 3 also. So traditionally till now we are using 0, 1, 2, 3 only. So let me write down 0, 1, 2 and 1 and 2. Okay, 0, 1 and 2. So ideally, if you consider the origin over here, okay, so I'm considering this is your x-axis. Okay, so if I consider the origin over here, so this will be, x will be called as x0 and its numerical value will be 0. Here x will be called as x1 and its numerical value is, let us say, some value is given to you. For example, this L1 is given to you as 150 millimeters, and let us say L2 is given to you as, let us say, 100 millimeters. Okay, so of course, if you use these values, so you will get 150 millimeters over here, and your x will be called as x2 at node number 2. So here 150 plus 100, so this value will be 250 millimeters. Okay, as far as your displacement is concerned, so here the value of u will be called as u0 and its numerical value will be 0 because there is a fixed support over here, and here u will be called as u1 and its numerical value will not be known because there is a load acting over here, and here the value of u will be called as u2 and its numerical value will be 0. Okay, so this is the free body diagram, and if you apply the boundary condition, so if you apply the boundary condition, so at, say, point 0. Okay, so at point 0 x will be called as x0, its numerical value is 0. At the same time u will be called as u0, its numerical value is 0. So this expression, okay, so this expression will be now 0 equals to a0 plus a1 into x value will be 0 plus a2 into 0 square. So if you solve this, you are going to get a0 value as 0, so that now your u expression will become a1 into x plus a2 into x square. Okay, then if you apply the second boundary condition, okay, so the second boundary condition is let us say at point 2. Okay, so at point 2 x will be called as x2 and its numerical value is 250, but your u value will be called as u2 and its numerical value is 0. Okay, so now if you substitute this over here, so this will be 0 equals to a1 into x is x2, which is 250 now, plus a2 into your x square, this is 250 square. Okay, so now if you solve this, okay, so if you solve this, so what you can do, you can have a relationship between a1 and a2, as this will be minus 250 into a2. Is it right? बराबर है ये? So this a1 and a2 we have now relationship, so now we can rewrite this expression as u equals to a1. So a1 is minus 250 times a2 into x plus you have a2 into x square. Okay, so this is the basic expression for the displacement polynomial, right? So now ultimately we are interested in finding out the strain energy. Now in case of bar element, okay, so I'm talking about bars over here, so your strain energy u can be calculated as a simple expression ae divided by 2, this will be integration over the length, okay, into we have du by dx whole square into dx. Okay, so for this purpose, first of all we need to have what is the du by dx, so we can have a derivative of this. So let us go for du by dx equals to, so here you will have only minus 250 into a2 because x will be cancelled over here, and this will be 2 times a2 into x. So this is nothing but your du by dx over here. Okay, so if you want, you can even take out your a2 outside, so you can write the same expression in a way something like a2 into, this is minus 250, okay, plus 2 times x. Okay, so this is a2 is a constant, so we can take it outside over here, right? So now if you substitute these values over here, now there will be a problem, because you see your a and e, it is not constant. So while deriving this particular expression, that is expression for the strain energy, we have assumed the value of ae was not changing throughout the length. Okay, so ideally if you remember initially, this value, that this a into e divided by 2, it was inside. Okay, but since it is constant, that's why we have taken it outside. So this is a square into dx. Okay, so now you see this a is changing. So now in this particular case, what you will have to do, now you see your a is constant from 0 to 150 millimeters. Okay, so now you will have now two expression. One is the expression, okay, wherein you may be having something like you have say a e, so this will be 1 divided by 2. Now here in place of this length, over the length, in place of over the length, it will be from 0 to 150. Okay, because this is valid only from 0 to say 150 only. And then you have du by dx whole square plus, now you have ae by 2, but this time you will be having a2. Okay, because this a2 term is coming from 150 to 250. Okay, so this is the length, so the here lower limit will be 150 mm and the upper limit will be 250 mm. Okay, and then you have du by dx whole square into dx. Here also dx will appear over here. Okay, so if you have a varying cross section area, in that case you have to break the limits into 2 parts or maybe 3 parts depending on the type of the problem. Okay, so it is, if it is a varying cross section area, you go for A1 and A2. If it is a varying modulus of elasticity, in that case you may have to go for E1 and E2 also. Okay, so in this particular way, now you have to analyze this the problem. Okay, so you can have U value as, let us say, AE divided by 2. So I'm assuming the the value of A is not given over here. Okay, so it is given in terms of this area of this particular section is twice A, and the area of this section is only A. Okay, so in place of this A1, now I'm writing twice A, okay, into E divided by 2. This will be from 0 to 150, and your du by dx now can be written as A2 into minus 250 plus 2x into dx. Okay, so this is the first part. Then your A2 is the area of the second element, and it is given in terms of A as simple A. So here you will have A, okay, E will be constant divided by 2. Integration, now this will be from 150 to 250 millimeters, and your expression of integration inside it will be remaining same, that is A2 minus 250 plus 2 times x over dx. Okay, is it okay to everybody? Is there any questions? समझ में आ रहा है? Yes, students, somebody please respond.
Yes, sir.
Okay, so this is how you have to go for the two different how to solve the problem using varying cross section area. Okay, so if you have different E, you can use different E also in this particular way. Okay, now so I am not completing this problem. Okay, so you can complete this problem by your own. I just wanted to tell you how to deal with the multiple values of areas when you are dealing with the when you are solving with the Rayleigh Ritz method. Okay, and this part, that is the loading part, that is the work done part. So work done part will remain same. So in this particular case only, this will be having minus of W1 into P1, that is the load or the deformation at point number 1 multiplied by the load which is acting at point number 1. So you have already calculated the value of the deformation, or this is the expression for the deformation. So in this expression, all we have to do is substitute the value of x as 150, isn't it? Because at that particular point, that is point number 1, the value of x is 150. So all we have to do is just write minus sign over here, and you have a displacement. So displacement function is minus 250 into A2 into x plus A2 into x square. This is the function. Okay, so all we have to do is just write in place of x this as 150, and this is 150 square multiplied by P. So now if you see the P value, so P is 3 kilonewton. Okay, so 3 kilonewton, and it is acting in the direction of the positive x-axis. So all we have to do is you just have to write down over here as plus 3000. Okay, why I'm writing 3000? I am converting this into newtons. Okay, so now you have the strain energy expression, we have a work done expression. So you have to solve this. Okay, this is not solved. Okay, so after solving this, you just have to go for the total potential energy pi is equal to say strain energy plus work done, and here you will find everything is there in terms of A2. Okay, so here also you will find there is a A2 term over here. Okay, there is a A2 term over here in the strain energy, and in the work done also there is a A2 term over here. Okay, so finally this will be there in terms of A2. Okay, so in order to maintain the equilibrium, you just have to go for d pi by dA2. Okay, so d pi by dA2, this should be 0. So you do this, what you are going to get after solving, you are going to get the value of A2. Okay, and once the value of A2 is known, you can solve this. Okay, is it okay to everybody? Yes, students, is it okay?
Yes, sir.
Yes,
Fine.
sir.
Okay, so this was the first part which I wanted to tell you in the case of Rayleigh Ritz method. Let me take another example over here. Now let us talk about the beam part. Okay, so let me draw a straight line over here. So now let us consider the beam portion now. Okay, so if I have a simple beam, okay, so this is my simple beam, right? And we have a simply supported beam. So this is a hinge support over here, and there is a roller support over here. And let us assume that there is a UDL. Okay, we have not taken care of the UDL over here in the while we are solving the problems of beam. So we have taken only the point load. We have not taken the UDL load, and we have not taken the volume load also. Okay, so so here in this particular case, what you can do is we can assume this as your x-axis. Okay, so this will be your x-axis and this will be your w-axis. Okay, so you can assume any displacement polynomial like w equals to a0 plus a1x plus a2x square plus a3 x to the power 3, and so on. If you require, you can go for a few more, this one, that is the uh, coefficients in the w. Okay, so here you can apply the boundary conditions. Okay, so let us say this is point number 1. Okay, oh sorry, this will be point number 0, not point number 1. Okay, so let us apply the boundary conditions over here. So let us call this as point number 0. Okay, at the center I can have point number 1, and here I can have point number 2. Okay, so we already know some of the boundary condition, that is at 0 we have w value as 0. At the L value, okay, so let us consider this is your length. Okay, so let us say this is your length. Okay, so this is your length. Okay, so at L you have w value is 0 because there is a roller support over here, and at L by 2, okay, that is at the point number 1. Okay, so at point number 1 we have theta equals to 0. So there are 3 boundary conditions. Okay, so we can utilize this 3 boundary condition, and you can rewrite the value of displacement polynomial w. Okay, so you can get these values. Okay, and then you can get this strain energy expression, that is EI divided by 2 integration over the length. This will be d square w by dx square whole square into dx. Okay, so I hope you can do this. Okay, now the only part is how to handle the load. Okay, so here the load is basically w. Okay, so this is a uniformly distributed load over here. So let us focus only on the w part. So your work done w can be of point load, it can be a surface load, or it can be even a volume load. Okay, so as far as this part is concerned, there is no point load, there is no volume load, so only the surface load is coming into picture. So usually what we write is this is minus integration over the surface, this will be u transpose. Okay, u transpose into you have ds. Okay, so now in case of beam, your ds is nothing but your surface. So we can have the ds value can be written as 1 into dx. Okay, so every surface, let us say if you convert, if you have the periphery of this particular beam, so I am assuming this periphery as 1 and this as L. Okay, so easily you can have the ds value as 1 into dx. So you can have this w. Okay, this is capital W, so this is minus. So now integration of over the surface, now it will become over the length, and here ds will become now dx. Okay, and it has to be of course multiplied by 1, and I think I have missed one more term over here, that is the fs, and then over ds. Okay, so we can have this u transpose multiplied by fs. Okay, so this fs value is nothing but your udl value. Okay, so as far as this part is concerned, the value of udl is given to you as w. Okay, and this u transpose is nothing but your displacement polynomial. Okay, so I should not write u, I should write w over here because this is beam. Okay, so this will be w transpose. So here after this is what we have assumed over here, you have applied these 3 boundary conditions, and finally you have obtained this w. So whatever value of whatever expression of w is there, that you have to substitute over here, So for example, so this is just an example I'm taking over here. So this W can be, let us say, minus, this is over the length. This can be, let us say, 200 into A2 into X plus 400 into A3 into X square. This could be, this is a random value I'm taking. Okay, so when you solve a problem, you'll get some values over here. And let us say the value of W is 10 kilonewtons per meter, and this will be dx. Okay, so like this you have to solve this, and at the end you are going to get the value of W in terms of A2 and in terms of A3. Here you have some value, here also you will have some value. So then finally again you have to do the same thing, that is the total potential energy is the sum of strain energy plus work done. Okay, so here this expression will be in terms of A2 and A3. You have to just solve it, you will get the value of A2 and A3, and then you can substitute in the problem, and then you can see the correctness of the solution. Okay, I hope this is clear to everybody, how to take care of this sulfate or maybe a UDL over here. Is it okay? Yes, students, is it okay? Have you understood this?
सर यूडीएल को पॉइंट लोड में कन्वर्ट करने की जरूरत नहीं है?
नहीं है, बिल्कुल नहीं है, because this is your surface load. Okay, because if you convert this into point load, then you have to find out what is the deformation at that particular point. यहाँ पर तो हमारा point है ही नहीं, so we have to just whatever expression is there, the same expression you have to write down over here. Okay, so like I said ना कि you are assuming this W over here. Okay, तो यहाँ पर तुम्हारा जो भी W assume करोगे, उसके बाद जो भी बाउंड्री कंडीशंस डालोगे, उसके बाद जो तुम्हारा W आएगा, so that W expression will be there. So this expression I have written over here. This is a sample or random expression, you can say. Okay, so this will be something like this. Okay, something like this. So this entire expression you have to put in case of W transpose in case of surface load. I hope this is clear to everybody.
सर ट्रिग्नोमेट्रिक फंक्शन से यूज कर सकते हैं क्या?
बिल्कुल कर सकते हैं, कोई प्रॉब्लम नहीं।
सर वहाँ पे फिर अननोन भी थोड़े कम आएंगे ना?
अननोन की क्वांटिटीज कम आएंगी वहां पर, बराबर है।
यस सर,
ठीक है, ओके, शैल आई कंटिन्यू?
यस सर।
Okay, now about the volume load, so we have covered this part. Okay, so now I'm just continuing over here. So work done is, let us say, only having the volume load. Let us say the sulfate is there. Okay, so if you have a sulfate, so this volume load can be written as integration over the volume. This will be W transpose into FV into dV. Okay, so now whenever you are dealing with the volume load, so volume load is nothing but your density. Okay, so whatever value of W is there, okay, the way we have handled the UDL, so same thing you have to follow, and you are at the end you are going to end up with some expression of W. Okay, so all we have to do is this capital W can be written as minus, this will be some, let us say, 200 into X times A2 plus 400 into say A3 into X square. Okay, तो ऐसा कुछ आएगा, है ना? So this is what I am writing randomly over here, and here this FV, so FV into dV, this will be slightly changed over here. Okay, so this is force over the volume. Okay, so this is nothing but say if you take a density of concrete, so this will be 25 kilonewtons per meter cube. Okay, and your dV, so dV is nothing but your area into x, that is dx. Okay, so all we have to do is just write the value of Fe over here as 25. Okay, and if the cross section area of the beam is given to you, so let us say area of the beam is given to you as 100 millimeter square, for example, so you can write this value over here into dx, and if this is not given, in that case you can always assume this value as unity. Okay, and since we have writing in place of dv we are writing dx, so this will be integrated over the length now. Okay, so in this way you have to convert the volume load into in form of a UDL, you can say, and then you can continue ahead. Okay, is it understood to everybody? Is there any questions? Please let me know. Yes students, is it okay?
सर जैसे एरिया का मतलब 1 into dx किया था, तो फिर dv का dx स्क्वायर नहीं होगा सर?
सॉरी,
जैसे एरिया का 1 into dx किया था,
हाँ,
वैसे अगर एरिया का वैल्यू अगर यहाँ पे पुट कर दिया 1 इंटू डी एक्स, तो dv इज इक्वल टू 1 इंटू डी एक्स स्क्वायर।
dx स्क्वायर कैसे आएगा बेटा? dv है ना।
हाँ।
जनरली तुम्हारा क्या होता है कि वॉल्यूम क्या होता है? सो वॉल्यूम इज नथिंग बट एरिया इंटू लेंथ, बराबर है?
यस सर।
बराबर है ना। तो अगर तुमको इसको पार्शियल डेरिवेटिव लेना है तो dv will be area is constant and this will become dx. Okay, so if you have a beam, okay, जिसका area constant है like this, so this expression is valid over here. So if area is also changing, then this value will be changing. Okay,
यस सर।
is there any other question please? Yes student, shall I continue then? Yes.
Yes, sir.
Fine. So from my side, I have covered every aspects of this Rayleigh Ritz method, and now the Rayleigh Ritz method is complete. So entire portion is now covered. So I'll be giving you one assignment on Rayleigh Ritz method, and you have to submit that particular assignment within the deadline. Okay, and it will be uploaded in the Google Classroom. I am planning to give 6 assignments. So the assessment scheme will be exactly same as the assessment scheme which we have seen in the last semester, that is for subject engineering computational technique. Okay, so you have 6 assignments which will be carrying, let us say, 30 marks, and we have 30 marks test 1 and test 2. Okay, so total will be 60. Okay, is it clear to everybody now, assessment scheme and all? Okay, so now I'm starting with the brand new topic, and we will start with the actual finite element method now. Okay, so let me create a new tab. So this is say 1D. Okay, so now I'm going for the bar element. Today we are going to see only the derivation part. Okay, so how to generate a stiffness matrix for a simple bar element using the finite element method approach. So this part we will see, and in the tomorrow's class we will see the numerical part. Okay, so let us start with the simple assumption. So let us say we have a simple element. Okay, so let me draw the bar element over here. So this is my bar element. Okay, and I'm assuming that there are 2 nodes to the bar element. Okay, remember in the orientation class I told you we can have a number of nodes in between also. Okay, so I'm assuming that this is the length of the element over here. So this is the starting point and this is the ending point. Okay, so this is the length of the element. I'm calling this node as node number 1, and I'm calling this as node number 2. Okay, so this is what I am assuming. At the same time, I'm assuming that the area is constant. Okay, so area is constant. So area is not at all changing if you move from node number 1 to node number 2. So with this, now we have to generate the stiffness matrix. So let us start the derivation of the stiffness matrix over here. Here I am also assuming that the E value, that is modulus of elasticity, is also constant. Okay, both the values I am assuming this as a constant, right? So now this finite element method is very much similar to Rayleigh Ritz method, you can say. So if you remember, whenever we are solving a problem using Rayleigh Ritz method, we have to assume the displacement polynomial. Okay, so now in this case also I'm going to assume the displacement polynomial. Again, I'm saying I'm assuming this. Okay, so this is totally based on the assumption over here. Okay, so I'm assuming the displacement as u, and this u can be written in form of a plus b into x. So this is my assumption. Even I can add cx square plus dx to the power 3. This is up to me, but right now I am assuming this over this only. Okay, so now let us apply the boundary conditions now. So at node number 1, what will be the value of x? It will be only x1. I don't know its value because I am just going for a derivation. Okay, at node number 2, what will be the x value? It will be x2 value. Numerical value is not yet known to me. Okay, as far as the deformation is concerned, the u value will be called as u1, its numerical value, again it is not known to me, and here u will be called as u2, again its numerical value is also not known to me. Okay, so now how to do this? So we have already assumed the value of u as a plus b into x. Okay, so now let us apply the boundary condition. Okay, so let me apply the boundary condition. Let me write down over here, that is apply boundary conditions. Okay, so the very first boundary condition which is known to me is at node 1. Okay, so at node 1 x will be called as x1, okay, and u will be called as u1. Okay, so this is already known to me, right? So now if you write this values over here, in that case what is going to happen? So every element has got some origin. Okay, so like here I have not mentioned the origin over here, so let us consider this as your origin. Okay, and this is your x-axis. Okay, so if I consider this as origin and this as your positive x-axis, in that particular case your x1 value will be 0 and your x2 value will be L. Okay, is it okay? So now with this assumption, now you can always keep the value of x which is called as x1. Now this value will be 0, but your u will be called as u1. Okay, so now if I have assumed this u as a plus b1 b into x, so this expression, if you substitute the values over here, so this will become u1. Okay, this will be a plus b into this will be 0. Okay, so simply if you solve this, so what you are going to get, the value of a, that is the unknown constant, is nothing but your u1, where u1 is nothing but the deformation at node number 1. Okay, so this is nothing but a deformation at node number 1. So now if you substitute these values in the expression, okay, so before going for substitution of these values over here, so let me write down the expression of this u. Okay, so this u value now will be called as u is equal to a1. In place of a1, now you have u1 plus b1 into x. Sorry, not b1, only b into x. Okay, so this is the expression for the deformation. Okay, so now let us apply the another boundary condition, that is at node 2. At node 2, x will be called as x2 and its value will be L, and u will be called as u2. Okay, I don't know the value of u2. So if you substitute these values in the expression which is over here, so this will be called as u2, this will be u1 plus b into x. So x value is nothing but your L, right? So if you solve this, okay, so if you solve this, what you can do is you can take this u2 over here and then divide it by L. So simply you can get the value of b as u2 minus u1 divided by L. Okay, so basically what we have done over here is we have found out the constants, that is unknown constant a and b. They are now in terms of u2 and u1. Okay, so if you refer your earlier original deformation expression, so earlier deformation expression was like this. Okay, so it was u equals to a1 plus b into x. So this original expression now will become, this will be u1 plus your b is nothing but u2 minus u1 divided by L into x. Okay, so now if you go for the solution of this one, okay, so let me expand some of the terms over here. So this is u will be now u1 plus this will be u2 by L into x minus u1 upon L into x. Okay, so let us take out these common terms of u1 and u2. So in that particular case, u will become, this is 1 minus 1 upon L. Okay, this will be into u1. Okay, So you can have this u1 outside, okay, and I think this should be x, not L1. This should be x, okay. Or let me rewrite it in a proper way. So this should be x, okay, and then we can have plus. You will have, say, this will be, sorry, this will be x upon L into u2. Is it correct? Yes, students, is it correct?
Yes, sir.
Fine. So now you refer two expressions, okay. So this was my first expression and this is my second expression, okay. So now what we have assumed? We have assumed the value of u, okay. So this is a expression which is showing you the overall deformation of the structure. So this was depending on x, okay. This is the meaning of this, okay. But now if you see this expression, so now you see this u is now depending on u1 as well as it is depending on the value of u2, okay. So depending on the u1 and u2, the entire expression is going to get changed, okay. So now you can rewrite this expression. You can rewrite the same expression as u equals to n1 u1 plus n2 u2, where what is your n1? So n1 will be something like 1 minus x upon L, and your n2 will be x upon L. These two things, they are called as shape functions, and they are the most important part in the finite element method, okay. So the entire expression is now changed. So initially the u was depending on this x, okay, but now if you refer this expression, this u is now depending on the nodal deformation, that is u1 and u2, okay. So now this is the nodal this is the shape function for two noded bar element. Remember, we are doing this, all these calculations for the two noded bar element. Now let us quickly see the variation of this n1 and n2, okay. So if you see the variation, so let me draw a straight line over here. So this is a straight line for n1 and this is another straight line for n2, okay. Let me draw one more line over here, okay. So now I have over here, so here we have x equals to 0 and here we have x equals to L. Here also we have x equals to 0 and here also we have x equals to L, okay. So now in this n1 equation, if you substitute x as 0, what is going to happen? You are going to get the value of n1 as 1, like this, okay. And if you substitute the x value as L over here, so n1 value will be 0, okay. So all we have to do is join this with the help of a straight line, okay. So with this now you can get the value of you can see the variation in the n1. So this is nothing but your 1 value and this value is nothing but your 0. So this is the variation of n1, okay. Similarly, if you substitute the values in the expression of n2 expression is very simple. It is simply x by L. So if you substitute x value as 0, you are going to get 0, and if you substitute x as L, you are going to get the value of this as 1 over here, like this, okay. So all we have to do is just draw a straight line which is something like this, okay. So you can see this value is 1 and this value is 0, and this is the variation of n2, okay. So now what is the meaning of this? So the meaning of this is the value of n1, okay. So the value of n1 is 1 at node number 1, okay. Remember, your x is 0 at node number 1 and value of n2 is 1 at node number 2. So this means the value of shape function is always 1 at the respective node. For example, if you have 3 nodes, it's 1, 2 and 3, so the value of n1 will be always 1 at node number 1. The value of n2 will be always 1 at node number 2. Value of n3 will be always 1 as at node number 3. So at that respective node, the value of n1 will be always 1. At the same time, if you see the other nodes, like for example n1 value, so the n1 value at node number 1 it will be 1, but at the other nodes it will be always 0. So same thing you can see with n2 also. So at n2, at node number 2 n2 value is 1, but at node number 1 the value of n2 is always 0. So these are the one of the two basic properties of the shape function. Again I am repeating, the value of node, value of shape function is always 1 at that respective node, and its value is always 0 at the other nodes. Okay, so if it is 1 2 3, so n1 will be 1 at 1, n2 will be 1 at 2, n3 will be node 1 at 3. At other points it will be always 0. There is one more property of the shape function, that the sum of shape function, so let us say sum of n1 plus n2, this is always 1. Okay, तुम्हारे पास कितने भी shape function हो, whether you have n1 n2 n3 n4, if you go for summation of all the shape functions, it is always 1. So let us try this. What is the value of n1 over here? 1 minus x, sorry, this is 1 minus x upon L, isn't it? So this is x upon L, plus your n2 is x upon L. So this gets cancelled, and what you are going to get is always 1. So this is third property of the shape function, that it is always the sum of all the shape functions, it is always 1. Okay, so always remember this. These are the shape functions, and they play a very important role in case of finite element analysis. Okay, is it understood to everybody? Please respond. Yes, students, is it okay?
Yes, sir.
Okay, fine. So let us quickly write the expressions. So in case of finite element method, we generally write the entire thing in form of a matrix. Okay, so the same expression, okay, let me write down this one. Okay, so the same expression, this u now can be written in form of a matrix, that is n1 n2, okay, multiplied by, you have u1 and u2. Okay, now remember always over here, these are what, these u1 and u2, they are nothing but what, nodal displacements. Okay, these are the nodal displacement, and this is what, this is nothing but your shape functions. Okay, so now if this is u, if this is u, you can calculate the value of strain, isn't it? So value of strain, how we generally calculate value of strain? Strain is nothing but du by dx, a very simple expression, right? So right now your u is nothing but n1 u1 plus n2 u2. So we are writing the same thing over here in form of a matrix, and here we are writing in terms of a expression over here. Okay, so if you want to calculate the strain, so here only one dimensional strain will be there, so this will be strain in x direction. So this is du by dx. Now this will take a shape something like d by dx of n1 and d by dx of n2, okay, multiplied by, you have u1 and u2. Okay, because you see u1 and u2, they are nodal displacement, they cannot be derived. Only n1 and n2 can be derived, because n1 and n2, they have the terms of x. Okay, so if you go for this, let us say, let me go down slightly. So if I go with d by dx of n1, so this is nothing but d by dx of n1. So n1 value, if you remember, we have calculated 1 upon x upon L. So if you go for a derivative of this, in that particular case, what you are going to get, it is nothing but minus 1 upon L. Okay, so this is the shape function. Okay, sorry, this is the first derivative. Then we have d by dx of n2 is nothing but d by dx of x upon L. So this is nothing but 1 upon L over here. Okay, so you can write the same expression over here now. So this is strain is equal to, now we have minus 1 upon L, 1 upon L into, this is u1 and u2. Okay, is it okay? So here you see we have here, this is nothing but your strain. Okay, and here we have displacement. Okay, so this particular matrix, okay, so this particular matrix is generally denoted by a symbol called as B, and this matrix is called as strain displacement matrix. Okay, so this also plays a very important role in the finite element method. Okay, so basically this shows a relationship between the strain and the displacement over here. Okay, now remember, in the Rayleigh Ritz method, what we have done, we have gone for pi equals to the strain energy plus work done. Okay, so we can have this total potential energy should be 0. Okay, so we can have d pi by dA2 equals to 0 and so on. So depending on the A1 and A2 and A3, so with the help of the principle of minimum potential energy, you can derive a simple expression. You can find this derivation in any of the standard FEM books. So if time is there, I will cover that one also. So in the standard textbook, what you will find, using this principle of minimum potential energy, this stiffness matrix K, okay, this is derived by a simple expression, that is V, integration over the V. This will be B transpose into D into B over dV. Okay, तो इसमें ये जो B है, this B is nothing but your this B. Okay, so this B is nothing but your strain displacement matrix. Okay, your D is nothing but your constitutive matrix. Okay, so this is called as constitutive matrix. Okay, so generally it shows a relationship between stress, okay, equals to D, okay, into strain. Okay, so this is simply a stress strain matrix. It is also called as a constitutive matrix. So now in case of 1D problem, you have only sigma x and you have only strain in x direction. So this value is nothing but a simple E. Okay, so if you remember theory of elasticity, in that you have sigma x, sigma y, sigma z, tau xy, tau yz and tau xz, all those terms will be there. But since we are dealing with only the 1D problem, so this particular expression will be sigma x is nothing but E into epsilon x. So your D value is nothing but basically your E, simple E, that is the modulus of elasticity. Again, in case of a 1D problem, the value of dV is nothing but 1 into dx. Here I am assuming this as constant area. Okay, so I am assuming that it's a uniform area. So you can have the one value, and if the value of area is given, in that case your dV can be written as A into dx. Okay, so now I can rewrite this K expression. So this is stiffness matrix. So this will be, now I am writing integration over the length. Okay, your B transpose. So just now we have calculated the B value. So B value is minus 1 upon L and 1 upon L. So if you rewrite the expression in terms of its transpose, so its transpose will be something like this. This will be minus 1 upon L. This will be 1 upon L. Okay, so this is B transpose. Your D value is nothing but your simple E value. Your B value is minus 1 upon L, 1 upon L. Okay, and then dV can be written as A into dx. Okay, so simply your K now can be calculated as, I am taking out A and E outside because it is constant over here. So all you have a multiplication of two matrices, minus 1 upon L, 1 upon L over here, and this will be minus 1 upon L and 1 upon L over here into dx. Okay, so if you go for the multiplication of these two vectors, okay, one is the transpose and one is the straight one. So if you rewrite this, so in that particular case you can have something like A E. Of course this will be integration over the length. So this is integration over the length, and here you might get something like 1 by L square. This is minus 1 by L square. This will be minus 1 by L square, and this will be 1 by L square. Okay, and this will be into dx. Okay, so now if I take out L square common, so in that particular case the value of K will be A E upon L square. This is integration over the length, here you have 1 minus 1 minus 1 1 into dx. Okay, and again if you solve this, so what you are going to get is ae upon l square, and here if you go for integration, here you will get l, here you will get minus l and l. So 1 l is going to get cancelled over here, so this is nothing but ae upon l, 1 minus 1 minus 1 1. So this is nothing but your stiffness matrix for the simple bar element. Okay, I think you have already seen this matrix in the matrix method when we have studied the bar problem. Okay, so ultimately at the end you are going to get the same matrix, but the approach is now different. It is finite element method based approach. Okay, so once the value of this k is known, you can go for the n number of k. So let us say if we have a bar problem in which there are 2-3 sections, so we can generate k1 k2 k3 k4 and so on, and then we can go for the assembly, and then we can solve the problem and you can get the value of stresses. So rest of the process is exactly same as the matrix method. Okay, I hope this is understood to everybody, the derivation part. Are there any questions, please? Yes, students, is there any questions? Yes, students, are there any questions? Or shall we terminate? Yes, students. Okay. So I'm guessing there are no questions. So I think we can wind up now. So that's all from my side. If you have any queries, you can remain in the meet.